Hi everyone, this is Ray from the University of Utah. Today I'm going to present our ASPLOS paper, the Analytical Characterization and Design Space Exploration for Optimization of CNNs. Our paper is focusing on optimizing the performance of the convolutional neural network. It is the core algorithm of many deep learning applications. The key operator of the CNN network is the count-to-the operator. It can be written as the following equation, and we can translate this equation to the following 70 loop nest. To optimize this code, the key question is, what is the design space of the optimization, especially on a multi-level cache architecture? We will use an example to demonstrate what is the design space of optimizing the count-to-the on a two-level cache system. On the left, we are showing our hardware hierarchy. The cache and the register compose the two-level cache system, and we also have a memory to hold all the data. We will create a 70 loop nest for the register, a 70 loop nest for cache, and another 70 loop nest for the memory. We notice that the loop order in the register level does not change the data movement, and we will consider all the permutations in the cache level and memory level, as well as the 14 different tile size variables. This will compose a very large design space, and finding the optimal code version in such a large design space is very difficult. However, in this paper, we propose a method that can find the optimal loop configuration by comprehensively analyzing the full design space. We will briefly introduce some key ideas and contributions in our work. The first contribution is the modeling and the pruning method. The idea is we are generating the symbolic expression for data movement volume of each loop permutation first. Then we will use the symbolic analysis to identify those inferior permutations and prune them out. The second contribution is we found a practical way to obtain the tile sizes that minimize the data movement volume for each retained permutation. This is achieved by formalizing and solving a constraint nonlinear optimization problem. The last but not least, we are creating a high-performance code generator to generate the count-to-the code. The idea is we are integrating the microkernel into our loop configuration to obtain optimization on both cache level and the instruction level. We will then present our experiment results. We conduct our experiment over 32 different count-to-the operators coming from ResNet, MobileNet, and Ulonet 1000. We measure the performance on two different architectures. We use the following items to compose our performance comparison. The first one is the performance of Intel 1DN library. The second one is the performance of the AutoTVM compiler. The third one, MOpt1, is we are using our model to select the best loop configuration and measure the performance. The last one, MOpt5, is we are using our model to select top 5 code version and report the best performance among those 5. We present our performance comparison in these figures. The x-axis represents different benchmarks. The y-axis represents the relative speedup over TVM. Overall, we are achieving more than 1.15x geomean speedup versus 1DN and more than 1.35x versus TVM. In conclusion, we propose a new approach to solve the design space exploring problem in optimizing the count-to-the. We create an effective analytical modeling approach to model the data movement and prune the design space. We demonstrate the strength of our method by comparing the performance with the state-of-the-art. We would like to thank the reviewers, the audience, and the funding bodies who are supporting our research. Thanks for listening. Please leave questions.